before, right? So last class we talked about the properties of the density matrix, right? And what are the properties? The first thing is that their trace equals to 1. If you try to think about when it is diagonalized, right, then each of the elements represents the probability of getting a particular pure state, right, or particular state. So they need to be summed to 1. And that's why the trace must be 1. That's the first thing, right? Second thing is that how do we know that it's a density matrix? Trace equal to 1, yeah, but what else is that these two means that they are positive semi-definite, PSD, right? First, it is Hermitian. Another is that all its eigenvalues are larger or equal to 1. We also learned how to distinguish the pure state density matrix versus the mixed state density matrix. The pure state one must be, its square has the trace equal to 1, because if you diagonalize it, you expect that it's going to have all 0 in the diagonal. Only one entry is 0. So if you do the square, you still have 1. So the trace has to be 1. But when it is a mixed state, at least it should at least have 2. For example, this is maybe 0.5 and 0.5. At least 2 entries. So none of them is 1, right? Then you take the square root, you sum them, then it must be less than 1. Right? So that is a way to memorize. And then we talk about why density matrix is useful, because if you try to find the expectation value of a certain operator on some of the pure state, on some of the mixed states, right? We have pi, we have k entries of this pure state to form the mixed state. Each of them have a probability of pi, and this is how you get the expectation value. We did not prove it because of time, but if you want, I can send you, or you just look up it from the internet. This is just equal to the trace of this operator times this quantity, and this is the quantity we have been using, right? So I have a typo here, right? This is pi, not pk, right? This is pi. We run from I to k, right? And this turnout is the density matrix, right? So you find the trace of their products, then it is the expectation value. And we again remember, this is like what? This is like the dot product, right? So, I mean the inner product, although we did not put the dagger, but a little bit similar, right? Or I can swap it, I can put the row in front, then that is the inner product, right? This is just equals to, I could have defined it as TR row M, right? And of course, this is just equal to TM dagger, row dagger M, right? Because row is Hermitian as a density matrix. So this is just the inner product of them. And then as a result, you see that you get the expectation value there. So there's some meaning there, right? Because finding the inner product, there is the expectation. If there's no inner product, we don't have overlap in the space, then the expectation value will be 0, something like that.